Welcome. In this session, we'll learn why are we using sine waves to express any other waveform in terms of sine waves. So why are we expressing the waveforms in terms of sine? Let's start. Now, before I proceed, in the previous session, we learned we can express any signal x of t or x of n as a weighted sum of these sine waves. Now, remember, we can use complex exponential waveforms or we can use cosine waveform as well. So on, and we saw if we use more number of terms in this, we can get approximation becomes better than we saw with the scale wave approximation. So we can write it like this as a summation, and this summation is annual. So this is the concept of this Fourier. So now why are we expressing x of t as a weighted sum of sinusoids? That's the point that we will illustrate here. Now there are several reasons for this, and I will listed few. Now, the first point or first important reason that why are we expressing the signals in terms of sine waves and what is so important about these sine waves? Now, the first reason behind this is because sine wave is a single frequency. So, the first reason is because sine wave is a single frequency. Now, how do we know that? Sine wave is a single frequency. If I see the time domain version of this signal, if I plot it, and if I plot it from this equal to 0, we can plot it like this, and this is time. So this is our x of t, or simply let me say this is our sine wave. So this is our sine wave. Right. Now in the frequency domain, and if we see the Fourier analysis or the frequency plot of this or Fourier transform of this, the Fourier transform of this looks something like this. So this is the Fourier transform of the sine wave. If we say this is sine omega naught t, then this impulse will occur at omega naught. This is omega, and the rest of the frequencies will be zero. That's the meaning of sine is a single frequency. Means it is non-zero only at one point, and the rest of the frequencies are zero. That's the meaning of its waveform of single frequency. Means it has one frequency in it, and we know if for mathematical convenience we also plot the negative frequency spectrum, and this will be at minus omega. Means the rest of the negative frequencies will be zero. That's the meaning of it's a single frequency. That's the literal meaning of it's a single frequency. Means the Fourier transform of sine wave is simply and that impulse at omega, and that omega is omega naught. That's the literal meaning of this sine is single frequency. So what will happen if this is a single frequency? So why is this important? What is so important about it's a single frequency? What will happen because of now? Go back to the approximation. When we approximate x of t as a weighted sum of these sinusoids, and we know this sine has frequency omega 1, this sinusoid has frequency omega 2, and this sinusoid has frequency omega 3. When we combine these sinusoids and express x of t and with some amplitude, now this amplitude actually determines how much content of omega 1 is present in this x of t. Remember that. So when we express x of t like this sine omega 1 t plus a2 sine omega 2t plus a3 sine omega 3t. Now see this amplitude actually determines how much content of this sine wave is contained in this x of t. Same way this a2 determines how much content of this frequency omega 2 is contained in x of t. Same way a3 determines how much content of omega 3 is contained in this extra right. So these amplitudes actually determine the content of the frequency that's contained in. So if this a0, a1, a2 and a3 are non-zero, what it tells you actually simply informs that this frequency is present. If a0, a1 is non-zero, If A2 is non-zero, then this is present and this is present. In other words, when we express x of t as a weighted sum of these sinusoids, this indirectly informs us which frequency is present in the signal. So this gives us the frequency domain information of the signal. Means this tells us the frequency content of the signal. Means why? Because this sine wave it will be a signal of single frequency omega 1. So if A1 is non-zero, that means omega 1 is present. Same too. If A2 is non-zero, that means omega 2 is present. Same way, if A3 is non-zero, that means omega 3 is present. As we know, a sine wave is a single frequency. So if this is our sine wave, this has a frequency omega naught. That's how we check that. This is the frequency spectrum of this sine wave. So that's why, because sine wave is a single frequency, when we express x of t as a weighted sum of sinusoids, this tells us the frequency content of the signal, means which frequency is present in the signal. So when we express x of t as a weighted sum of sinusoids, this gives us the frequency information of the signal. That's why we do Fourier analysis, means to get the frequency information of the signal. That's why we do Fourier analysis. So that's why we are expressing this a signal as a weighted sum of sinusoids, and this is the first important. Because sine is a single frequency, this will give us the, when we express x of t as a very weighted sum of sinusoids, this will give us the frequency content or the frequency information of the signal, which frequency is present in the x of t. For example, in the previous session, we approximate x of t as a weighted sum of sinusoids like this. It was like this, if I remember it correctly, by 3. I don't remember it correctly. I think I will. Please check it like this. So when we do this, that means omega 1 is present, that is having an amplitude of 4 by pi. Same way 3 omega is present, means this frequency is present in the square wave, and the amplitude of that square wave is 4 by pi times 3, means 4 by 3 pi. Same way this frequency 5 omega is present in that signal, and the amplitude of that content of that frequency is 4 by 5 pi, means we have 4 by pi here. Same way, there will be 7 omega here, and omega will be some fundamental frequency of this square wave. So square wave tells you that. And in other words, this tells you there are only odd harmonics or odd frequency components present in the square wave. So that's the first point. And having with a square wave with some frequency means this repetition point. This tells you which frequencies will be present. And this is the beauty about sine waves. When we express x of t as a weighted sum of sinusoids, this gives us the frequency information of the signal. That's why we do, as a communication engineers, why we do go for Fourier analysis, means to get the frequency information of the signal. Means as an electrical engineer, why we go for Fourier analysis? We want to get the frequency information of the signal. And the first important point is because sine wave is a single frequency, this will directly tell us the frequency content or the frequency information of the signal. So I hope this is clear. Now, second important reason why we go for Fourier analysis, or why we express x of t as a weighted sum of sine waves. Now, the second important reason is when we apply sine waves or sinusoids as input to the system, LTI system, when we apply sine waves, let me take an example, sine omega t plus theta, and suppose the amplitude is A. Now, when we apply this as input to the LTI system, the output of the system will simply be, there will be a change in amplitude. Suppose the amplitude changes to A1 sine omega t plus theta plus some phase. So what is this LTI system doing to this input? It's not changing the frequency. You can see the frequency is same. It's only changing the amplitude. Amplitude gets changed to A1, and it's modifying the phase, so it's not changing the frequency. Now depending upon how much, let's not worry about the phase, see, depending upon how much it changes the amplitude, it will tell you whether the sinusoid will be passed through by this LTI system or not. So if A1 is a non-zero, that means this sinusoid is passed by this signal. And when we say this sinusoid is passed by this LTI system, in other words, means this frequency is passed by this signal. Means this omega is passed by this LTI system. Means whether that system will pass this this LTI system or not, that will be determined by A1. If A1 is non-zero, means this omega is passed by this LTI system. So that's the second important reason. And when we express x of t as a weighted sum, of sinusoids, and we see the output will be simply like bi sine omega t plus some phase that will be involved by this, depending upon which, okay, this will be omega I when we express as a weighted sum. So depending upon which bi is non-zero, that will say that that omega I at the output is non-zero. Means if any bi is non-zero, that means that sinusoid is passed by this LTI system, means this will give us the bandwidth information of the system. Means if we want to do the analysis of the which signal is passed by this LTI system, when we express x of t as a weighted sum of these sinusoids, what, and we want to see how the system processes or passes these sinusoids. And when we do that, we know the system output will look like this. This is true. Remember, this is true in terms of networks as well. This is always true. But depending upon which coefficient is non-zero, that means that sinusoid is passed by this signal, passed by this system, sorry, passed by this LTI system. And based on that, we say that frequency is passed. Why? Because we know a sine wave is a single frequency, and when that sine wave at the output has some amplitude, in that system is passed. And this tells us how the system behaves for a particular frequency. Means this will also, for a communication engineer, this will give what is the bandwidth of the system. So when you do this analysis, this will tell you what is the bandwidth of the system, whether the system behaves as a low pass, high pass, that you can get from this. That's why we express x of t as a weighted sum of sinusoids. So if we say that bi is non-zero, that means that omega I is passed by the system. So depending upon how much is the amplitude of bi, that will give you how omega I is passed by the system. Means what is the influence of the system on this frequency that you can get from this. And this is very, very important for communication engineers, for calculation of bandwidth, and for as an electrical engineer. This is very, very important for machine design. When we express x of t as a weighted sum of sinusoids, so this is referred as expressing x of t as a sum of fundamental component and the harmonics. Means we say machine, electrical machinery, we say this is expressing x of t as a sum of fundamental component plus harmonics. In machines, we say it like this. Means electrical machine, like induction machine, electrical motors are synchronous machine. When we do this, we say we are expressing x of t as a fundamental component plus a harmonics. And when we apply this as input to the system now, we say, and we want to study the impact of the harmonics on the machine. And this helps us actually to see what is the impact of these harmonics on the machine. For example, on the induction motor, what is how it impacts the speed, or you say power generation in synchronous machine. So that's why we are expressing, we use sinusoids. We are expressing that x of t as a weighted sum of sinusoid. That's the beauty of sine waves using sine waves. I hope it's clear. This is the rough idea why there are several reasons actually. I have given just reading. First reason is the sine wave is a single frequency. This will give us the this will tell us the frequency content of the signal. So that's the first important point. Second is when we apply sine wave as an input to the system, and this is referred as a steady state response of the system, and thus LTI system does not change the frequency, it only changes the amplitude and phase. It modifies only the amplitude and the phase. So if it's an LTI system or a network, it only changes the amplitude or phase of this. And depending upon how the amplitude is changed or how the phase is modified by the system, we say whether the signal or the simply the frequency is passed by that system. So for a communication engineer, we say whether the signal will be passed by the system or not. If the output amplitude is non-zero, we say that omega is passed, and depending on how much amplitude we have at the output, we say how it modifies the given frequency. And this is very, very important for electrical machinery. This is very, very important for electrical machinery. When we express x of t as a sum of fundamental component and the harmonics, and we want to see the impact of these harmonics on the machine, like on induction machine. If it's an induction machine, we want to see what is the impact of this these harmonics on the speed. Or same way, if it's a synchronous machine, we want to see how much is the impact of these frequencies on the power generation. That's how we do it. That's why we do it. Right? So for communication engineer, we want to see the how what is the frequency content or simply the bandwidth of the system we want to. That's why we do for Fourier analysis. And this is the actually the backbone of frequency domain analysis. Why are we going for this representation? Means why we express x of t as a weighted sum of sinusoids, because we want to see the frequency content of the system or how the system processes a given sine wave. So if we want to do this system analysis, you express x of t as a weighted sum of sinusoids and apply that as input to the system and see how it processes the. So I hope you have got the concept. This is very brief. There are several reasons I have just given you. So please go through these points again and again. You will get the concept. In the next session, we'll learn the different representation of Fourier analysis.